So in this type of problem, we're really trying to optimize this two variable function here. And it might look complicated because there's a comma in here, f of x comma y. But really all we're going to be doing is we're going to be plugging in a point in here, like maybe 1, 3. You'll plug in a 1 in for x, a 3 in for y, you see what you get out. So we're going to focus and graph these three things first. So graphing this first line, x plus y is less than or equal to -1. X-intercept of -1, y-intercept of -1. It's done by that cover-up method. And then since it says or equal to, I'm going to make a solid line through those points. Ugh, that's not so good. Then we'll graph this one too. This one in green here has an x-intercept of -4.5. And if you're wondering where I'm getting these quick dots from, it's the cover-up method. I'm pretending this isn't here, and it says 2x equals -9. So I divide 2 from both sides. So -4.5 is what you get for that one. So I dot on -4.5 for the x, and then we can cover up the x variable to find out the y-intercept. The y-intercept should be -3. And then this third line, x is greater than or equal to -6. Well, x equals -6 is a dotted line, a solid line, sorry. 1, 2, 3, 4, 5, 6, over here, roughly. And if it's saying greater than, it just means we're eventually going to be shading in this direction, so we'll make a note there. So we got to find out where to shade for the other lines. And to figure out where to shade, you can always do it by a test point. Like with this red line, maybe we're supposed to shade up here. And if we are, 0, 0 should make a valid solution. But if you plug in 0 plus 0, you get 0 is less than or equal to -1. That's not true. So that means we don't shade this way, but the red line is supposed to go down over here. So it's probably going to be this area in between, but we want to check too by checking the green line. Looking at the green line, we're either going to shave up here for the green line, or we're going to shave down below the green line. And if you plug in 0, 0 in for the green line, you get 0 is greater than or equal to -9. So that's true, so the green line is telling us to shade up. So indeed, the area we need to shade is in between these three, this right here. So to optimize this, we've got to find out which of the vertices gives us the biggest amount. So like this is going to be a vertex. We need to find out exactly what the coordinates are of the intersection. This is going to be a vertex. And then somewhere down here, the red line and the green line are going to cross. So we need to find out exactly what that is. And that's the harder of the two. So let's start with that. So my red line and my green line, let's put those guys together off to the side. And if you solve it like a system of equations, that will tell you the intersection. So if you remember solving systems of equations, to find out where these guys cross, oops, I hit the wrong button. To find out where those two guys intersect each other, we can solve it with the elimination method. I'm going to multiply the whole top by -2. That way I'll have a -2x over a positive 2x, and I can just add the top line to the bottom line to make them cancel out. So now you can add them together, and those cancel out. -2y plus 3y makes 1y, and they get 2 plus -9, that makes -7. So that's the y coordinate of where they cross. And if you want the x coordinate, you just got to plug -7 back in for y. So x plus -7 makes -1. X would equal +6 there, because 6 plus -7 makes -1. So when you solve that as a system, you get 6 and -7. That's the coordinate for where these two lines cross. We'll want to write that down. While we're at it, let's find the other two. This one right here, where the red line crosses the blue line, that's again found by solving them as like a system. So we pretend that the signs in the middle are equals, because we're trying to find out where the exact line is, not where the shading goes. So this is telling us that x equals -6. So if you plug -6 up into this equation and solve for y, you're going to get +5 for y. So we say this crosses at -6, 5. Then do the same thing for the point down here. If you plug in -6 into the green equation for x, you get -12 plus 3y equals -9. You add 12 to both sides, so you get 3y equals -3. In other words, you get y is 1. Just checking that, 12. Yeah, that's right. -6, 1 is the other. So we have all three of the vertices for where they cross. Okay, -6, 5, -6, 1, and 6, -7. So if the question you're asked is to maximize this relationship, you're going to plug all 3 points in here and see which one gives you the biggest value. If it's asking you to minimize, though, you obviously just do the opposite. You plug them all and see which one's the smallest. So let's say your problem is asking you to maximize it. I'm going to take the first pair that I found, 6, -7, and plug it in. So we get 6, -7. Plug that in. Plugged in a 6 in for x, a -7 in for y. So we get -60, and then -12 times 7 gives us a positive 84. So combine those, you get 24. So that's our first value. Let's plug in the next vertice, -6, 5. If you plug that in, -6 in for x here, and then 5 in for y. Get -60 minus 60. So that gives you -120. So far, if we're asked to maximize, 6, -7 is the winner. Last one we haven't tested was -6, 1. So if you plug that in, -6 in for x, 1 in for y. Whoops, I just realized I made a mistake up here. I forgot to plug in a -6. That's why that was so low. So that would give us a positive 60 here. So it gives us 0 for this one. Same thing down here. It's -10 times -6 subtracted by 12 times our y coordinate this time was a positive 1. So when you simplify this one, you get 60 minus 12. So it gives you 48. So there's our winner right there. -6, 1 is the maximum of these. We had 24, we had 0, and we had 48. So -6, 0 maximizes this relationship.